My topic is reduction potential. Now, I'm not teaching you reduction potential. That's more like AP chemistry, but it is a property, and I can teach from that property. I can teach the periodic nature of atomic behavior. So reduction potential. First of all, I need to tell you what that is. That's the first thing. So in chemistry, there is a drive for atoms to achieve electrical stability. And there's only a few atoms on the periodic table that have achieved that electrical stability. We call them the noble gases. They're the gases on the far right of the periodic table. They have S2P6 on the outside, and for some reason that appears to produce the lowest energy state of electrons around a nucleus on the outside. So all the other elements to the left of the noble gases are not stable. Now, they may be relatively stable because we've learned that having a half full sublevel, such as a D5 or a P3, that may lend some degree of stability, or they may have a full sublevel, such as a D10 or an F14 or an S2. But the ultimate stability would be S2P6. And so when atoms are flying around and colliding into each other, their electrons are getting sloshed around. It's like if you were running through the hallway with 2 buckets of water and bumping into people, your water would splash onto people and their water would splash onto you. These electrons are getting sloshed around in all these collisions. It's happening billions of times a second all around us, in the air, even on the surface. If you have a banana or an apple sliced on the table, you'll notice it's turning brown, and that's because millions of times a second these collisions with oxygen atoms are occurring. And as the oxygens bump into the carbohydrates that make up that, partly make up that fruit, the electrons get sloshed onto the oxygen. The oxygen, like, thank you very much, and it changes the electron structure of the apple, the banana, whatever. And therefore, because the electron structure changes, and that's where light comes from. All light comes from falling electrons. Remember that line? Did I write it up there? Maybe not. No. Well, I've said it. And so if you change the electrons, then the ones that are falling are going to change. And so the light that's being reflected is going to change, and the color change. That's a pretty good indicator of a chemical reaction. So these collisions are happening millions of times a second. And those atoms that do not yet have S2P6 may end up getting them by bumping into another atom hard enough so that its electrons momentarily slosh over into the domain of that atom. And that atom goes, thank you very much, I'll take them. Or maybe the other atom wants to get rid of its outer electrons because maybe like sodium, number 11, maybe it's S1, and that's very unstable, and it's just too far to go to expect an atom to get 7 extra electrons to make S2P6. So if it just loses that 1 electron underneath those 11 electrons, or underneath that outermost 1 electron, there are 10 perfectly arranged electrons that are organized the same way neon is. So sodium, if it collides with another atom, instead of taking electrons, it's like, please take mine. It goes over to whatever, and sodium stabilizes. So the tendency of an element to gain an electron is known as the reduction potential. And that data table that I showed you, of which this graph is made from, is a graph of the elements from 1, in my case, from elements 1 through 18, and their tendency to gain electrons. We could have been talking about tendency to lose electrons. There's tables for that as well. Now, we have a little saying in chemistry, that oxidation is loss of an electron and reduction is gain of electrons, or just oil rig, if you think of it. Platform that they use to drill for oil. Mostly now it's on the ocean because we've pretty much drilled out all the land-based oil. But oil rig, you used to know what those things were. It's a mnemonic. Oxidation is loss, reduction is gain. So the reduction potential, now what I'm doing is I'm modeling for you what I want you to do with your property. You're defining it, you're explaining it to the class so that the class can understand your property, because it's going to be on a quiz in the next week or 2. So reduction potential is a measure of the element's tendency to gain an electron. Now, why is gaining called reduction? Because electrons are negative. So if you gain an electron, your charge is reduced. If you're neutral and you gain an electron, your charge is reduced to -1, right? So notice, starting off with lithium, number 3, hydrogen is, there's hydrogen. Why isn't hydrogen connected? You'll notice that all of the noble gases are missing. Noble gases won't gain electrons. They've already got a full S2P6 perfect complement of electrons. You'll notice probably for many of your properties that the noble gases are missing, because in a lot of cases, the properties are chemical properties, and therefore noble gases don't behave chemically. They're inert. They have their S2P6. They're not trying to get 8. They have 8, so they don't participate in chemical reactions. So it's difficult to measure a chemical property for something that doesn't behave chemically. All right, so we're missing helium. We're missing neon. So it jumps from hydrogen down here to lithium. And therefore, hydrogen is all by itself on energy level 1, and you cannot describe a trend with 1 point. So we're going to ignore hydrogen. We'll start with lithium, and it's easy to see lithium on energy level 2. When you give your talk, I want you to do this. You can say the word energy level. You can say the word shell, because I know that you Google these things, search them up. But I want you to understand, and I want you to do your best to try to talk about layers of electrons, because that's what energy levels are. They are the layers of electrons. So energy level 1 are the elements with just 1 layer of electrons. This is energy level 2, starting off with lithium and ending here with fluorine, skipping neon, because it's not a chemically active element. That means all of these elements have 2 layers of electrons, the inner S layer, 1s layer, and the outer 2s2p layer. So this is really, even though I call it energy level 2, it simply is referring to the elements that only have 2 layers of electrons, and this would be energy level 3, those elements that have 3 layers of electrons. So on energy level 2, or of the elements with only 2 layers of electrons, we start with lithium, and you'll see that its potential is -3. In other words, lithium has a very low potential to gain an electron. And if you think about it, you can understand why. I'm going to talk about valence electrons, which is the assignment. Connect the valence electrons to the visible trend. The trend is that as you move across the period, as you move from lithium to fluorine, the potential increases. On average, the potential is increasing. So why might an element with only 1 valence electron not have a potential to gain electrons? Because they're, again, the S2P6 is favored energetically. I'm trying not to be anthropomorphic. If I were anthropomorphic, I would say because lithium wants 8 and it can't really get 8 by gaining. It can only get 8 by losing. And actually, lithium won't get 8. It's got 3 valence electrons. If you remove 1, lithium will become like helium, S2. In order for helium to become like neon, it would have to gain 7 more electrons. That's not likely. With 1 valence electron, in order to get 8 by gaining, you'd have to gain 7. And the reality is you don't have enough proton pulling power to grab 7 consecutive electrons and pull them around and hold them around yourself. You just don't have enough stickiness that way. So what ends up happening with 1 electron, 1 valence electron atoms, they don't gain 7, they tend to lose 1. And underneath that 1 electron is the inner energy level that is already full. It was full, so it moved on to the next energy level and put 1 in the S1 position. But underneath that is a full. Now, it doesn't matter whether you talk about lithium or whether you talk about sodium. They're both S1, and they both have 1 valence electron, and they both therefore have the lowest potential to gain electrons in their respective period. So of all the elements that have 3 layers of electrons, sodium has the least potential because it only has 1 valence electron. And you can say the same thing for those that have 2. 6 electrons is a lot of electrons to gain. So instead of S2s gaining, they tend to lose as well. S2 would be 2 valence electrons. Then we have S2P1. That's 3 valence electrons. Now notice we're getting closer to 0 potential, which is like neutral. Like, I can take it or leave it. I don't care, So now we have S2P2. That's 1, 2, 3, 4 valence electrons. 4 is halfway to 8. So it can gain or lose with equal, it's seemingly with equal ease. And you can see that it is a little bit higher than 0. So it actually, carbon has a little bit more likelihood of gaining an electron, it seems, from this data, than losing an electron. Now, I said that the general trend across the period is increasing likelihood, increasing potential to gain electrons. I'm going to skip the little squiggle here because we got to come back and talk about that. Look at fluorine with 7 valence electrons. Super high. It's got as much potential to gain an electron almost as lithium didn't. Every now and then you go to McDonald's and you get your large fries, your large soda, your Big Mac or whatever, and you'll notice there's a little sticker on the soda cup or the burger box or on the fry box, and you peel it off and it's like, oh, Virginia Gardens, it's McDonald's Monopoly, let's play, right? Maybe I'll win $1 million. Well, the first time you play it, maybe you think that, but after you have eaten at McDonald's for a couple years and played it once a year and realized I'm never going to win. You stop caring about those little Monopoly pieces and you leave them on the tray and throw it away because you know you're probably not going to win. Now imagine one day you get down and you have your meal and you pull off the stickers, and let's say you need 4. Let's say you need 4 of a particular color, the green one. I think it's 3, but we'll say it's 4. And let's say you've got 3. You pull off your soda, you pull off your burger box, you pull off your fry box, and you've got 3 of the same color, and you're only 1 away from being a millionaire. Guess what you're doing, Jose? You go into the dumpster and you're going to climb in the dumpster and find that one, right? Or you buy 10 more, or you go to the next table and say, excuse me, you want that? Excuse me, you want that? And you start caring, right? You're like driven. You're motivated because you're 1 away from being a millionaire. And that's kind of like fluorine. Fluorine has such a high potential for gaining electron because it's 1 away from being a millionaire atomically. S2P6, 8. So it has a very high potential. It's very motivated to get that extra electron. Here we have S2P4, 6 valence electrons. It's also fairly motivated. But then look at this, S2P3. Why is P3 less likely to gain an electron than even P2? It seems like this should just be a straight line, right? Why is that little squiggle there? What is it about P3 that means it doesn't want to change? Because that's really what that's saying. It wants to change less than the one before it. It wants to change less than the one before to the one after it. That's a little, that we call that an energy valley. That's a little valley that things could roll into and remain temporarily. Now we've seen that somewhere before. There it is. It's the energy curve. It's like a mountain. When you're up at the top of the mountain, you're very unstable because you have a lot of potential to change. And these elements are trying to get to S2P6 down here, the milk gas configuration. Now they can fall all the way and release a tremendous amount of energy at one time. That would be like an explosion, a very reactive substance. Or sometimes they, in their bumpings and collisions, they can bump their way there and find temporary semi-stable positions to rest. Nitrite is like that. Nitrite, it's pretty reactive material, but it won't necessarily blow up unless you do something to it. Now, if you have fish in an aquarium, the fish excrete nitrite, and it's a poison. It kills other fish and when it accumulates. So you put these little drops in your aquarium, and it converts the nitrite to nitrate, which is less toxic to fish. And so nitrite might be here. Nitrate would be here. Maybe nitrite is here, nitrate's here. Nitrate is a fairly stable version of nitrogen. Nitrite is not. It still has potential to cause harm. But here we see that P3 is semi-stable. So let's go back. All right, so this is P3. P3 doesn't want to change. It's that half full sublevel, which means we can read this graph here. It tells us that there is some stability. It has a little resistance to change. It would cost energy to lose an electron. It would cost energy to gain an electron. It's going to stay right there. Now, when we go to period 3, energy level 3, or those elements that have 3 layers of electrons, we see a very similar curve, although it seems to have shrunk a little bit. And we see that there's another squiggle right there around the P3. The fact that the energy well, the dip, the valley, actually occurs at P4. But it's something similar going on. There's a resistance to move from a nearly half full P sublevel to going back or even to go forward. So let's talk about, let's nail it down with the valence electron. 1 valence electron, very low potential. 2, increasing potential, pretty much all the way to the end to 7 valence electron. The big surprise here, which maybe isn't a surprise, is that when you have P3, which is S2P3, 5 valence electrons, you reach a little semi-stable state. It looks like it appears over there as well. The halogens, column 17, have the highest potential to gain electron. The alkali or period group 1 metals are the least likely to gain. 1 valence electron elements are least likely to gain. 7 valence electrons atoms. 7 valence electron atoms are most likely to gain. Single valence electron atoms are least likely to gain. And that's what I'm looking for. Label the high points, look at the trends. Here are the trends going down. As atoms get bigger, they're less likely to gain electrons. There's a reason for that. You go to the basketball court, and there's this skinny, muscular, six-pack guy. He's playing ball real close. Not yet. That was Eli, right? Eli liked to do that to me. So there's a skinny, muscular, six-pack guy, and he's dribbling the ball through his legs. You're never going to get it. You're never going to gain that electron from that guy. But if there's a big dopey guy out there bouncing the ball, you're going to be stealing from him all day. So the bigger the elements are, the less likely they can hold on to their electrons, the less likely they have ball control. The electrons are so far away from the thing pulling them that they lose them easily, and you can actually see that in the data. All right, so that's what I'm looking for, something like that.